Quick revision video on calculating the pH of a solution that contains a weak acid and a strong alkali. So I've got a couple of questions for you to try, so if you want to have a go at this one, pause the video and then play on when you're ready for the answer. So just as in the previous video where we had strong acid and strong alkali, we're going to do the same sort of thing. So the first thing we'll do is calculate the starting moles or initial moles of the chemicals involved. So we've got that many moles of acid, that many moles of alkali, and obviously we don't have any salt or water formed. And then at the end of the reaction, you can see the KOH is in excess, and so there'll be no acid left. There'll be the difference between these two numbers of moles of KOH left. And I've put these in as well, and this is going to be more relevant for the next example. But you would make that many moles of salt from the limiting reagent moles, and you'd make the same number of moles of water. So the important thing is the KOH is in excess by that many moles, and because it's monobasic, it's also the number of moles of OH minus ions. We're going to turn that into a concentration by dividing by the combined volume of 60 cm cubed, and then we're going to use the rearranged Kw expression to get the H plus concentration. And remember that Kw at that temperature of 25 degrees C is 1 times 10 to the minus 14. And then we just minus log that 5 times 10 to the minus 13 to get the pH of 12.30 to 2 decimal places. So here's the second one. It's a little bit trickier than the previous one, but if you want to have a go, pause the video and then play on when you're ready for the answer. So same as before, initial moles is those numbers there. Final moles, at the end of the reaction, we've got those numbers there. So the important thing to note in this one is the weak acid, the propanoic acid in this case, is in excess by 0.017 moles. So before I go into the rest of the calculation, I just want to use a different slide to make an important point. So if you remember back to how you calculate the H plus concentration of a weak acid on its own, you've got the dissociation, that's the generic dissociation of a monobasic weak acid. So HA is in equilibrium with H plus and A minus. So in that beaker, you've got all of those species present, and Ka is the H plus concentration times the A minus concentration all over HA, and because it's monobasic we say that the H plus concentration equals the A minus concentration, so we get that, and then to get H plus it's the square root of Ka multiplied by the HA concentration. And if you can remember, the HA concentration we approximate to the original concentration of the acid due to the tiny amount of dissociation that takes place. Now the question that we're in the middle of at the moment is we're calculating the H plus concentration of a weak acid that's in excess from a reaction with a strong base. So we haven't just got this going on here, we've actually got this reaction's taken place. And the important thing to note is the HA concentration is going to be less than the original concentration of the acid because some of it's reacted, and the A minus concentration is going to be more than just from the dissociation because A minus is a product of the reaction. So we're still going to use the Ka expression for a weak acid, but we can't use the same method as when the weak acid's by itself because of what we've said here. So these aren't equal to each other because A minus is a product of the reaction, the salt being formed in the reaction, and the original concentration of the acid's gone down quite a bit actually because it's reacted with the OH minus ions. And obviously to get the H plus concentration we rearrange like that. So we'll go back to the question. We know that the weak acid's in excess by 0.017 moles. So there's the Ka expression for a weak acid. There's the rearranged equation for H plus concentration. And now we're just going to plug the numbers in. So obviously Ka is given in the question. the HA concentration, so the concentration of the acid at the end of the reaction, will be the moles left divided by the volume that they're in, so that's 0.017 over the combined volume of 150 cm cubed. So we've got that concentration for the weak acid. The salt ions, well, we'll have this many moles divided by that 150 cm cubed, so we've got that. So that gives us an H plus concentration of 2.87 times 10 to the minus 5, which we minus log to get the pH. So we get 4.54. So a bit trickier than a straightforward pH calculation, but hopefully that all made sense.